Hello and welcome to lecture number 13 of the course Robot Motion Planning. In the last class we looked at sampling based methods. Today we'll move on to the next method, which is potential field based methods. Okay, very quickly revising what we were doing in the last class. So in the last class we looked at the sampling based methods in which we don't search in the complete workspace of the robot and try and focus our search such that we get the path faster than the other methods like cell decomposition methods, etc. Okay, so very quick revision of sampling based methods. So in sampling based methods, basically we have the workspace and we have obstacles. So this is my workspace and there are obstacles here. So these are obstacles. Okay, and what we do is we have the robot, which is a point robot here, and we have my initial point here, and that's my goal point. Okay, so in this method what we do is we randomly explore a smaller subset of possibilities while keeping track of progress. Okay, that means I start looking at various nodes. So from my initial point I take my node here, and basically this node is whether it is possible to go to that point or not possible to go to that point, whether the robot can go to that point or not. So essentially what we do is we randomly explore a smaller subset of possibilities. For example, this is free space, it can go here. This is not free space inside the obstacle, so it cannot go there. Okay, then what we do is we make connections between these nodes, okay, by means of edges, and we make a connected graph. Okay, so we have a set of points, and then we connect the points with edges and see whether I can connect the initial point to the goal point. Okay, so if we do this, then what happens is that we do not explore the complete workspace, but we can get a path which is much faster, using an algorithm which can work in a much faster or lesser time. Okay, now so in the sampling based methods, one of the methods is probabilistic roadmap, in which we generate a graph which is given here, G, and where V is a vertex. So V is a vertex. This is also called a node, and E is an edge. Okay, so what is a vertex? Vertex is points where the robot can go. So these are points where the robot can go, and we connect these points by means of edges, and by connecting this by means of edges we make what is a connected graph. Okay, then what we do is basically we try, after we have made this set of connected graphs, we try and find if there is a path between the initial point and the goal point. Suppose my goal point is here. Okay, now this is basically the probabilistic roadmap method, by which it's a sampling based method, and in which we make a connected graph. Now the other way is rapidly exploring random trees, in which what we do is basically we have again a workspace and we have obstacles. So these are my obstacles, and the robot, let's say, is here. The starting point is here and the goal point is here. Okay, so this is my initial point and that's my goal point. Now in this case what we do is it is something similar to growing a tree. So this is the base of the tree, the roots of the tree, and the tree is growing branches like this. Okay, so it's almost same as the previous one, but the only difference being that this is a connected graph in the form of a tree, and then we see whether we can connect the goal. And once a branch connects the goal, then we know that there is a path which is taking it from here like this to the goal. Okay, this is basically what is called RRT. Now you can also grow the trees in two directions. For example, if you have a workspace in which we have an obstacle here, and this is my initial point and that's my goal point. So in this particular case what we are doing is we are growing the tree in two different directions. So there is one tree which is going from here, okay, like this. These are branches of the tree, and the tree is going out, and from the other direction another tree is coming. Okay, and then if they are meeting somewhere in between, then we know that okay, this is a meeting in between. So both the trees are meeting in between, and what we can do is we can search for a path which will take me from the initial point to the goal point. There can be one path, there can be more than one path. Okay. So what we see is in this sampling based methods, we don't search the whole workspace, but we basically look for a smaller subset of possibilities, which makes the search faster. But then we are sacrificing optimality, and you may not be able to find a path, even when a path can exist. So this is something we discussed in the last class. Now we'll move on today to the next method, which is called our so the next method is potential field based method. Now this is a directed search. Now what we mean by that is, in the previous case, if you look what we are doing here, we were generating these nodes randomly. Very often we were generating the nodes randomly. So I have a node here, I generate the next node which is here or here or here. Okay, so all these nodes are possible, but we are generating the nodes randomly. Okay, now there are of course directed ways of searching. For example, if you are going near an obstacle, then you should sample near an obstacle more than you sample in a free space. Okay, now in the directed graph methods, what we are doing is we are trying to direct the search, direct the search from where to where. So we are basically directing the search from the initial point to the goal point. Okay, just like we're trying to guide the robot from the initial point to the goal point. Okay, now how do we do that? Is basically we use the idea of a potential or a potential function. Now potential function, you would understand very easily. You have dealt with charges, for example. Okay, so we have a positive charge, so we have a plus charge and we have a minus charge. So if you have a plus charge and a minus charge, what would happen is these two charges will attract each other. Okay, so this will be attracting. And if you have a plus and a plus, or we have a minus and a minus, what will happen? This will repel. Okay, so these two charges, these two are going to repel each other. So now if I can assign potential or charges to the goal and the robot and the obstacle, then this attraction and repulsion can be made use of in directing the robot to go from the initial point to the goal point. Okay, so for example, if I have a robot which is standing here, so there is a robot, there's an obstacle, and there's a goal. So that's my goal and that's my initial point. So what I can do is I can give the robot a negative charge. I can give this also a negative charge. So what will happen? It will repel the robot, right? And I can give a positive charge here. So what is going to happen? The robot will get attracted towards the positive charge, and it will go like this towards the positive charge, get repelled by the negative charges, and then it will go towards the goal. So we are directing the robot towards the goal. Okay. Now, so one example is charged particles. This is an electrical potential. Okay, so this is an electrical potential. Now we can also have magnetic fields, okay, and have magnetic potential. So we can have magnetic potential. Now in case of north pole and north pole, north and north, they're going to repel, or south and south are going to repel. So these two are going to repel each other. Okay, this we know, this will repel. Now we can also have a north and a south, or a south and a north. Okay, now this is going to attract each other. They are going to attract. So basically we can place the north pole, the south pole on the robot or on the obstacle or on the goal accordingly, and ensure that the robot is attracted towards the goal and it is repelled by the similar charge on the obstacles. Okay, so this is the idea of using magnetic energy or magnetic potential. Now you can think about an elastic spring, okay, or a rubber band, and this electric spring has spring energy. So basically if I have a spring like this, okay, and one end is fixed, and I pull it, okay, and or I compress it, then F is equal to K into del x, small deflection, it deflects a little bit, and this is my del x. Now what it is storing? It is storing the spring energy. Okay, so the elastic spring or this tension spring, when you pull it or you compress it, it is storing potential energy. So when I leave the force, what will happen? The spring will come back to its original shape. Okay, so it is gaining the energy and it is giving back the energy in that way. Now you can also consider this to be gravity. There are different kinds of energy, as you know. So we can also consider this to be or this principle to work on magnetic energy. Sorry, not magnetic. We have already seen magnetic. We can look at gravitational energy. Okay, or G. So if you consider a ball, for example, a ball, okay, and the robot is sitting here. The robot is there, and this is a ball, and gravity is pulling it in that direction. Okay, now the robot is at the edge and the goal is at the center, let's say. Now, what would happen to the robot? Gravitational energy, gravity is going to attract the robot, and the robot will start rolling down. So it's like a ball. Okay, so this is like a ball which is sitting there. Okay. Now, what is happening is it was having a potential energy mgh. Okay, so as it is coming downwards, what is happening? It is losing potential energy. Okay, now the robot is coming down because gravity is pulling it down, and it is coming in. Where will it rest? It will rest at the goal. Okay, so in this configuration, the minimum energy is at the goal. Okay, now, so what is the direction in which it is moving? It is moving in a direction in which it is losing energy. It is losing potential energy. Okay, so if we talk in terms of the gradient, then we can say that it is following the negative gradient of the energy there. Okay, so the derivative of potential is force. Okay, now potential energy we can talk about in terms of electrical potential, we can talk in terms of magnetic potential, we can talk in terms of gravitational potential. Okay, now the derivative of potential is force in a particular direction. Okay, so this is something to remember here, that the derivative of potential is force in a particular direction, and force, we can take the force as velocity of the robot in this case. Okay, so the force is pulling the robot towards the goal, and the obstacle is repelling the robot away from the obstacle. Okay, and this can be taken as the velocity of the robot in this particular case. As we go along, it will become clearer. Now, the basic idea of a potential field method, of potential field method, is that the ball, the charge, spring, these are analogies, and these are ways of storing potential energy. Okay, so these are ways of storing potential energy, and they can be used to guide motion in a particular direction. So the robot moves to a lower energy configuration, as we saw in the case of the ball, that the robot was actually coming down. So it was mgh here, so that's my h. Okay, so the ball was rolling down and it was losing potential energy. Okay, so the robot moves to a lower energy configuration. Okay, so in this method, what we have to do is first is that we define a potential function u. Okay, so in this case, we are defining a potential function u, and energy is minimized by following the negative gradient of the potential energy function. So first I need to write a potential energy function which is u, and then I take the negative gradient of that, and the robot follows the negative gradient such that as it is moving, it is losing energy and moving towards the goal. Okay, now we can think of a vector field over the space of all q's, and q's are the configurations. Okay, so we can think of a vector field. Let's look at it this way. So these are various points, okay, which are the q's, the configurations in the workspace, and this is a vector field over the space of all q's. Now at every point in time, okay, let me mark it here. So at every point here, okay, the robot looks at the vector at that point and goes in that direction. So at this point here, okay, suppose this is my robot is here, initial point, this is my goal point. Now if the robot is being attracted by the goal, then the vector would be in this direction. Okay, because it is being attracted towards the goal. There's an attractive potential there. Okay, so at every point, the robot looks at the vector at that point and goes in that direction. Okay, so that is how basically how the potential field method works. First, we define a potential function, and we take the negative gradient of the potential energy function, and the robot looks at every point, it looks at the potential there and goes in the negative direction, so that it basically is reducing the potential energy. Okay, now in terms of force, okay, as we go along, we'll see more about this. Now let's see what are the various potential functions that we use and how it basically works. So we have an attractive potential and we have a repulsive potential field to guide the robot. Okay, now the attractive potential will move the robot towards the goal, and the repulsive potential will push the robot away from the obstacles. You can move to the goal, and this will avoid obstacles by pushing the robot away. Now, so the total potential at any point is the sum of the attractive potential plus the repulsive potential. Let's see, this is my initial point of the robot. This is my goal point. Okay, these 2 points, initial point, goal point. This is my obstacle. Okay, now let me assign charges to this. Let me assign negative charges. Okay, so these are all negative charges I'm assigning to my obstacle. And the robot has to be repelled by the obstacle, so the robot also I'm assigning a negative charge. But the robot has to be attracted towards the goal, so I have to assign a positive charge there. Okay, so now if you look at every point here, what is going to happen is that the robot is going to be pulled by the goal. In what direction? It will be a straight line like that. Okay, it will be attracted in that direction. But at the same time, at this point, there is an attractive force which is coming from the goal in that direction along the straight line. Now the obstacle is repelling it, the robot, with a force in that direction. So if this fellow is pulling it, that fellow is pushing it like that. Okay, so what is going to happen at this point is there is going to be a net resultant of the attractive force. This is my attractive force and this is my repulsive force. Okay, so what is going to happen at that point is the robot will be subjected to the vector sum of these 2 forces, okay, and it will go in the resultant direction. So if the repulsive force is more, it will push it away. If the attractive force is more, it will pull it towards the attractive force. Okay, so depending on the attractive force and the repulsive force, wherever is the resultant of the 2 forces, that is the direction in which the robot is going to go. Okay, now this is the basic idea of potential field method, which is a guided search. So the robot is being guided away from the obstacle and towards the goal. Okay, now so the first thing that we need to do is we need to assign an attractive potential and we have to assign a repulsive potential. Okay, so attractive potential should so let us assign an attractive potential. Let us define a function. So uq is the attractive potential, and the simplest is to have a function u which is equal to zeta into distance. D is distance between the robot and the goal. So let me put it this way. So this is my, let me just put it here. So this is my point q. It is in this configuration q, and this is q goal. Okay, so what is d? D is the distance between these 2. So that's my d. So this is the qx y, and let's say this is x goal and y goal. Okay, so d is the distance between the 2 configurations q and q goal. So my simplest potential function that I'm putting here is a conical potential where we have a constant zeta, where zeta is a constant and d is the distance, which is the distance between the. Now if this is the conical potential, then I need to find the gradient, okay, that is given by the grad of u. So the gradient of this, now let me see what is the distance between q and q goal. So d is equal to root over x minus x goal squared plus y minus y goal squared. This is the Euclidean distance. So I can write this as a raised to half, where this is equal to a, just to understand. Okay. So now when I'm taking the derivative of this conical potential, then there are 2 variables, there is x and there is y. Okay, so first I take a partial derivative with respect to x, then I take a partial derivative with respect to y. So if I write it that way, what do I get is del u by del x. So this is my del u by del x, which is equal to half a raised to half a raised to minus half 2 into x minus x goal. Similarly, I get del u by del y is equal to half a into minus half 2 into y minus y naught. Okay, now what will happen? This 2 will cancel, this 2 and this 2 will cancel, this and this will cancel. So what does this come out to be? Del u by, so del u by del x is equal to x minus x goal divided by d. D is q and q goal. Okay, so this is a actually. Okay, so that is my in distance a. Okay, so now du by dy is equal to y minus y goal divided by d again, q minus q goal. Okay, now this is what we have seen, that the grad of this will be equal to zeta by divided by d into q minus q goal. Okay, this is what we are seeing here. Okay, this and this for x and y. Now what do you see for this gradient of this conical potential is that number one is that it is proportional to zeta. So uq is directly proportional to zeta. Okay, it depends on the constant you put. So if you put a larger constant, the force is going to be more. If you put a smaller constant, the force is going to be less. Then it is inversely proportional to 1 by dq and q goal, which means that if dq q goal becomes equal to 0, this will go towards infinity. This will become infinity. That means when the robot reaches the goal, when robot reaches the goal, the grad u will go to become infinity. Okay, because the distance will become 0. So it is not defined at that point, not defined at goal. Okay, so if you use a conical potential, what we see is that the gradient is proportional to the constant zeta, and it is inversely proportional to the distance, which means that at the goal what will happen is it will become undefined. Okay, because the distance between the configuration and the goal will become 0. So if the conical potential doesn't work or there is a problem in the goal, what we do is we use a quadratic potential. We can use a quadratic potential. Now the quadratic potential, attractive potential, is written by half zeta d squared q and q goal. Okay, now in this case again zeta is a constant. Okay, so this is a constant, and d is the distance between the q and q goal, just like in the previous case, and the grad of the attractive potential, in this case the quadratic potential, is equal to, so d squared is equal to x minus x goal squared plus y minus y goal squared. Now again there are two variables, x and y, so variables are x and y, so we have to differentiate it twice. So what would happen is del u by del x would be equal to half, okay, half zeta into x minus x goal, sorry, x minus x goal into 2 will come here. Okay, and del u by del y is equal to 2 into half zeta into y minus y goal. So this 2 and 2 will cancel, and what will be left with is so in either case we'll be left with du by dx, which is equal to, so this is equal to zeta into x minus x goal, and du by dy will become equal to zeta by y minus y goal. Okay, so what we see here is that in this particular case it is zeta, which is a constant, so it is proportional to constant. So the larger the constant, the more the force, and it is also directly proportional to the distance. Okay, q minus q goal. Okay, so what we are seeing here is that in the case of the quadratic potential, it is defined at goal. So at the goal what will happen, this will become equal to 0. Okay, grad of u attractive will become equal to 0 at the goal. Okay, unlike in the previous case where this was not defined at the goal. Okay, so there is a problem, suddenly it goes to infinity, or if it comes very near the goal, this will start going towards infinity now. Whereas if you use a quadratic potential, then what happens is that it is directly proportional to the constant that we are assigning, plus it is directly proportional to the distance between the goal, and it is defined at the goal. Okay, unlike the conical potential. So one good idea would be to use both of them together. Okay, so combining potentials to avoid extremely large velocities. For example, the velocities grow with distance. This is something we have seen. Now combining two functions of conic and quadratic potentials, each active at a particular distance. Okay, so what we can do is we can assign a distance now, such that if I have my q here and I have my q goal here, okay, I can try and define a distance which is called q star. Okay, now here I can use zeta into d into q and q goal here, so I can use the conic fellow here. Okay, now the conic fellow, as it comes closer and closer to the goal, what will happen is there is a chance that the velocities will become very large. Okay, and it will become undefined at the goal. So what we can do after the distance, I say zeta squared d squared into q minus q goal. Okay, so at this distance what will happen is q star, so we have a particular distance at which there will be a switching over from the from the conic to the quadratic. Okay, so there will be a switch here at q star, and we can define this function. So what you can see here is that there is a constant here q which you have to define. Okay, second is you can define this distance q when you want the switch over to take place. Okay, now so much about the attractive potential, where we can have two potentials and they can be active at a particular distance. Now the repulsive potential, the repulsive potential should repel the robot, which is clear. Okay, now it should repel, but first of all that it should repel, which is fine. Okay, but if it starts repelling from very far distance, then what will happen? The distance, the path will become longer. Okay, let me take an example here. So this is my goal. Okay, and this is my initial point. Okay, and there's an obstacle here. Let's say there is now let me draw the goal here, and there's an obstacle here, and there's an obstacle here. Okay, now suppose I say it is attractive, it is plus, and this is minus, and this is minus, minus, minus. Okay, now what is going to happen is that the attractive fellow will have a force in which direction? In this direction. It will connect straight to the it will connect straight by a straight line. Okay, that is my attractive potential. It will attract it this side. Okay, and the repulsive potential will tend to repel this side. Okay, so what will happen is the two forces will have a resultant at this point, depending on their magnitudes, of course. Okay, so what will happen is the robot will not move in a straight line, but will tend to get pushed off like this. Why? Because there is a force. Let me draw it in some other color. There is one force in this direction, and there is another force which is normal to this in that direction. Okay, so what is going to happen is the robot is going to move in a resultant direction. So if I draw it like this, then depending on their magnitudes, the resultant of these two forces are in which direction? It is in this direction. Okay, depending on the magnitudes, of course. So now the robot is moving like this, like this, like this, like this, like this, like this, and then coming to the goal. It is reaching the goal, yes, but it has taken a longer path. Okay, so what we can do is we can ensure that the repulsive force does not repel the object at longer distances. Okay, but only when the robot comes very near the obstacle. Okay, so again we put a threshold distance which is q star, and say that the repulsive force will act only at q star. Otherwise there is no point, it will tend to push the robot away. So if this happens, that the repulsive force is active only here, then the robot will follow a straight line like this till here, then it will go like this, like this, like this, and then go to the goal. Now this path is shorter, you can see it very clearly. That fellow is longer. Okay, and because of which we use this q star as a distance. Again, it can be set by the person. Okay, there's nothing automatic here. It has to be set. Like you set a value of a constant, you can also set the distance here. That at this distance, let's say q star, this is my distance q star, the robot will start getting repelled. Okay, now what should be the repulsive potential? So we are saying the repulsive potential is half zeta 1 by d. 1 by d is the distance between robot and obstacle, and q is the distance, effective distance or active distance. So when this robot comes within the distance q, only then this is active, otherwise this force is inactive. Okay, so if this is my potential 1 by d minus 1 by d star squared. Okay, so this is my potential function I'm using. Now if I take the grad of this, what will be the grad of this? The grad of this is that zeta 1 by q star minus q d, and you get a 1 by d squared here. Okay, so what is happening here is that we are having a d star here, and this is coming in the denominator. So it basically means that it will become very large as you come nearer the obstacle, very large as you come near the obstacle. Okay, so as you are coming nearer and nearer to the obstacle, what is happening? This d squared, it is d squared. Okay, so the repulsive force is increasing very quickly. Okay, so this is the repulsive potential that we are using. Again, zeta is a constant, so the constant would mean that you have to assign the value of the constant. Now the total potential acting would be the sum of the attractive potential plus the repulsive potential. So here we are having the attractive potential, which is this way, so it is attracting the robot towards the goal. Okay, so it is increasing, as we can see that this is the attractive potential. This is the repulsive potential, which is repelling the object. Okay, and what will be the resultant of both of them? The attractive and the repulsive potential will be shown here. So this is the sum of the attractive potential and the repulsive potential. Okay, so suppose I want to go, this is my point, this is my goal, this is my initial point. So it will be going in this direction like this. As soon as it comes near the obstacle, it will avoid the obstacle and then go towards the goal. Okay, so let me draw it. It is going on the other side. Okay, so it's dashed line and going back. Okay, let me draw it here. This is my initial point. So it starts off towards the goal. This is my goal point. Starts off towards the goal. Then it starts avoiding this obstacle, comes that side, and then goes to the goal. It's going behind, in between these two obstacles actually. Okay, so here if I draw it in top view, so this is my top view. So there is here and there is here. So if the robot was, this is easier to understand. So if the goal was here and this is my initial point, then the robot will start going like this, then avoid, not so sharp, avoid like this, and then go to the goal. Okay, so it is going like this, then avoids like this, and then goes to the goal. Okay, so this is what we are seeing, how the attractive potential and the repulsive potential together affect the motion of the robot. Now we saw that there was a constant zeta and there was another eta. Okay, eta was for the repulsive potential and zeta was for the attractive potential in the potential functions that we used. Now these are constants, which mean that you have to assign them numerical values. So if you make them very large, now obviously the attractive potential should be larger. Okay, otherwise it won't attract. The repulsive potential will push it away. Okay, so these are some things which are logical, that the attractive potential should be larger than this should be larger than that one. And what about the numerical values? That depends now on the problem, how fast you want it to go. Okay, now the very simple way by which this method works is that it goes to the bottom of the potential, so it basically means it follows a gradient descent algorithm basically. Now if it is following a gradient descent algorithm, there is a question of a local minima or a global minima. Okay, so if you look at this case here, the robot is standing here. Let's say this is the profile. Okay, the robot is a robot is a ball, you can say. Now it is going down like this, decreasing potential energy, going like this, but once it comes here, it gets stuck. Okay, it does not have enough energy to overcome this one. Okay, now this is not a global minima, this is a local minima here now. Now whereas the global minima is somewhere here. Okay, so this is a problem that comes up with the potential field method, the question of getting caught in a local minima and not reaching the global solution. So there are critical points, maxima, minima, and saddle points. So this is a standard problem of potential field method. Any gradient descent algorithm has this problem, that it can get caught in local minimas. Now this pictorially shows the attractive potential field. Okay, we can imagine this to be charge, direction of charge. Okay, now if this is my goal, this is the center of the goal, let's say. So this is the goal and that's my center. Now what is the direction in which the lines of force would be moving? So they'll be moving normal to the surface like this, okay, towards the center, right? Like this, right? So we are seeing that this lines of force which are pulling in a particular direction are moving towards the center there. Okay, you can see that from okay, so they are moving in that direction. Okay, so this is the attractive potential field. So you can imagine that if there is only a attractive field here, it is pulling towards the center of the goal. Now what about the repulsive field? Now the repulsive field, if you can imagine it to be here, so this is repulsive. Let me take some other color. This is repulsive, it is here. It is forcing it in that direction, so it is going out in that direction. Okay, so it is forcing the robot away in that direction. So this is a repulsive potential field. Okay, so the sum of the two fields, this is an attractive potential field, this is a repulsive potential field. What will be the sum of both the attractive and the repulsive potential fields? So at every point in this vector field, there is going to be a vector which will be a resultant of these two fields. Okay, so if you're looking at an obstacle and this is a goal, suppose this is my robot. So the robot will be attracted in this direction. Okay, and as it is moving towards the goal, okay, what is happening as it is coming here, you can see this the vectors at these points are changing direction. As it is coming nearer and near the obstacle, it is changing direction. Okay, so it is coming here like this, and then going there. Okay, thus you can see very clearly. Now how far will it be? Like this? Will it be like this? Will it be like this? Which one? This depends on the values of zeta and eta. Okay, so if the attractive field is very much larger than the repulsive field, okay, then what will happen is it will go closer and closer to the obstacle and it will go almost like a straight line towards the goal. Okay. And also on your q star, which is the distance at which the repulsive field is active. Okay. So at every point in the workspace, there is a vector which is guiding the robot towards the goal and away from the obstacle. And the direction of the vector would depend on the numerical values of this zeta and the eta that we are going to assign. Okay. So this is the basic fundamental of, so you can see here, so if this is my distance, so if I say this is my q star, then the repulsive potential is active only in that q star. So the robot starts going now. Suppose the robot is here, so this is my initial point, that's my goal point. Then the robot starts going in a straight line towards the goal, okay, because that is the direction in which the vector is going. Then the moment it comes inside that effective area, then it starts getting repelled. It goes like this, and then goes in a straight line again. Okay, so here we see that it depends on zeta, it depends on eta, it depends on zeta, it depends on eta, and also q star. So when you're writing the program, basically you have to numerically tune these parameters depending on, and we'll see as we go along how do you tune these parameters using optimization. Okay, so this explains the potential field method, how it works, how potentials are assigned, and how the negative gradient of the potential is followed such that the robot can reach the goal. Now what we talked about is number one is local minima, number two is distance and gradient. Okay. So suppose I have an obstacle here like this, that's my obstacle. Okay, now a real robot would have sensors, so sensors like ultrasonic sensors. So sensors would mean ultrasonic sensors. So these ultrasonic sensors can find distance, and as you would be familiar with ultrasonic sensors, how it basically works is that there is a ceramic transducer. So there is a ceramic transducer here, okay, and so this is a piezo crystal, and the piezo crystal is actuated in a particular frequency. So in a particular frequency we give it actuation signals. Okay, so this is my piezo crystal. You know that in a piezo crystal what happens is if you give it charge, okay, it will expand. Okay, it'll expand a little bit. So what happens is, if you are giving it, this is my time axis and this is my voltage axis or charge. So what would happen here is, if I give it a charge, it will expand, and then I give this in a particular frequency. So this is my frequency, okay, and every time it expands an ultrasonic wave, it is expanding and contracting. So this wave will go out. So this is my ultrasonic wave. This wave goes out, hits an object, and then it comes back again. So it goes out. Now it comes back means it applies a pressure on the crystal now. And if it applies a pressure on the crystal, you produce a charge. It produces a charge because it's a piezo crystal, okay. So the moment the wave hits the piezo crystal, a small wave is produced here. So it has gone out. So this is going out. This, it has come in, okay. And if I see the distance between here to here, I see the time distance del t. I know the velocity of sound in air. I know exactly how far the obstacle is. Now how this works basically is, it is basically rotated in a particular direction, okay. So if we have a, if you can imagine that this sensor is mounted and it can rotate maybe 360 degrees or 180 degrees, 0 degrees to 180 degrees. It gives out these waves, and wherever the wave is hitting, it is basically it is giving the feedback that the obstacle is there. So you are being able to profile the profile of the object also. So ultrasonic sensors are used also to get the profile of the object, as well as to get the distance between the robot and the object. So this distance is the shortest distance that we are talking about. So this distance is the distance here that we talked about in the potential field function. Okay, so where's the d? Yeah, so this d. So this d is found by an ultrasonic sensor, how far the robot is from the obstacle. Now the right side basically gives us a distance, it gives us the example. So we have a robot q here, and there are obstacles q1, q2, q3, q4. So the ultrasonic sensor can scan, let's say from 0 degrees to 360 degrees, and it gives this distance metric, okay. So finding this distance metric, the robot can actually compute at that point what is the force, the repulsive force it is subjected to from the various obstacles, okay. Now computing the distance, if you have an ultrasonic sensor, is in the case of a real robot. Now suppose you are doing a simulation. If we are having a simulation in which you don't have a real robot, but I'm simulating the robot, obstacle and goal point. So what we can do is, we can use the bushfire algorithm. So we had looked at the bushfire algorithm earlier, in which we use a grid, and the bushfire algorithm actually is one way to find out the distance between the robot and the obstacles. So how this basically works is, the obstacles start with a 1 in the grid and free space is a 0. Okay, so let's look at this here. So this is my obstacle. So the obstacle is assigned 1, and we increment the next grid from this grid, sorry, the next square rather, by 1 unit. Okay, so if this is 1, then that is 2, and this is 2, then it's 3, 4, like that. We keep increasing. So these are all 1, so the next is going to be 2, 2, 2, 2. Next to the 2s will be 3, 3, 3, like that. Okay. Now if we cover the whole workspace like this, basically I can find out if my robot is here, then what is the distance between the robot and the obstacle. It is very easy. You need to just look at that number 7. Okay, that means that this is the metric of the distance between the robot and that obstacle now. So this is a very easy way of finding out what is the distance between the obstacle and the robot. That is my d in the form of a grid. Now in the case of a wavefront planner, okay, this is also a grid kind of a planner, in which we apply the bushfire algorithm starting from the goal. Okay, this is a little different way. In the earlier case, we were applying the number 1 to the obstacle, and then we are incrementing every grid by 1. Here we are saying that we are starting the bushfire algorithm from the goal, and yeah, we are applying the algorithm from the goal. Let's look at it how it goes. So here the obstacle is 1, and the goal point is marked as 2. okay, in the wavefront planner. Almost similar. Now from 2 we mark the next one is 3. So we increment from goal. In the previous case we were incrementing from the obstacle. So if this is 2, the next one is going to be 3. Okay. So if that is 3, then the next is going to be 4. So we're incrementing it this way. And what you see is that we are covering all the full workspace. Okay. So this is my goal. This is my robot, which is at 0 there. Okay. An obstacle is marked 1. So robot is there and this is my obstacle. Okay. So now we have incremented the whole workspace, and what we are seeing is that we are incrementing it this way, and we have finished the complete covering all the grids. Now it is called a wavefront planner because it moves like waves on water. Okay, the way if you drop a stone on a surface of a pond or a lake, then what would happen, the disturbance will generate waves, and the waves are going to move outwards. So it is similar to that, which we call a wavefront planner. It moves like waves. Now if you look at this, now you can find out using gradient descent again. Okay, so what this robot has to do, basically it is using gradient descent. That means it is choosing the lesser number. So if it is 18, it has to choose the next number which is smaller than 18. So it is choosing 17. Okay, so it is let's go back here. So it is choosing this one, 10, 9. So from 9 it will come to 8, 8 will come to 7, 7 to 6, in that way. Okay. So basically what it is doing is it is choosing numbers, it is using gradient descent, and it is going in choosing numbers which is smaller than itself. And this is one path it finds. Now there is another path which can find, it can be like this. Okay. Then the next question is which path it will take. Okay, which one is faster. Okay. So this was basically finding using gradient, so gradient, negative gradient. Okay. So this is one way of finding out the distance in case of a simulation. If you don't have a real robot where you are actually computing the distances. Now we talked about the potential field method, which is susceptible to this problem of local minima because it's a gradient based method. So what can happen is it can get caught in a local minima and it appears that it is the goal, but it is not really the goal. Okay. And these are, in terms of path planning, these are called traps. So how to avoid traps due to local minima? Number one is, suppose we have a local minima this way. Let's look at a case here. Okay, I have my goal point here. So this is my goal and this is the initial point. Now the attractive force from the goal will be in this direction, so it will move like this. Okay. Now when it is going like this, what would happen is it will get caught here, because at this point what is happening, the repulsive and the attractive maybe at this point is becoming same in the same direction, so they will cancel each other. So what would happen is the resultant force is equal to 0. Okay. Once the resultant force is equal to 0, means the robot is not moving anymore. It is not subjected to any force. So it is caught here or it is trapped. Okay. Now let us look at another example here. Let's look at this example. So this is very common in path planning problems. A U-shaped kind of an obstacle. The robot is here. Initial point, goal point. The robot moves in a straight line, and at some location what is happening, the attractive force which is pulling it and the repulsive force which is coming from here are going to become 0, and the net force is 0 now. Now the robot is caught there. Okay, because the net force is 0, so it doesn't move in any direction. Okay. Now this can also happen if you have a set of obstacles, say one obstacle here, another obstacle here, and this is my goal. Same thing happens. So it is pulling in this direction, it is forcing it in that direction. So at some point it will become resultant, become 0. So in such case, what can be done is we can give a tangential force. We can give a tangential force at this point. We subject it to a force which is tangent to the surface here. So I give a tangential force here, and this tangential force moves the robot in that direction. Okay, again it tries to go here, again it is forced in that direction by a tangential force, and finally it goes like this and goes to the goal. So we subject the robot to a tangential force once it gets caught in a trap. Okay. Similarly here we can give it a small force like this and comes this side. Now the other way could be to give a random disturbance. Suppose I have, let me take this example again. Okay, so the robot has got caught here. This is my goal point, this is my initial point. The robot has got caught there. So what we can do, we can give it a disturbance force, a small random disturbance. So I kick the robot that side, small force. So from here the robot goes there. Now again it goes there, now it tries again. Okay, it may not be able to get out, but this is one way of disturbing it and trying so that it can try again. Okay. The other way of avoiding traps is a new random start point. For example, I have an obstacle which is of this shape. Okay, and this is my goal point, and this is my initial point. So what is happening here is it is coming till here and is getting caught here. So the moment it gets caught, I can give it a new random start point. It is almost similar to giving it a disturbance. So from here I start the algorithm again, and from here I push it here, so it comes there. Okay, so this is a random start point. I push it from there to here. Now it starts again. Okay, it may be able to overcome, may not be able to overcome. Now if it gets caught here, I give it another point, it goes there. Okay, so it could be random, so it could be here also. Okay, now you may be able to get out, you may not be able to get out. Now the other way of is by looking at, you should also be able to circular traps. So this circular trap is very common again in potential field method, where we have an obstacle which is of this nature, and the robot is moving from here, the initial point, to the goal point, and this is my straight line. Okay, so it comes here, it gets stuck. Let's say it comes here, it gets stuck. Okay, now this is my repulsive and this is my attractive. It gets caught there. So I move it, it is following the tangential force, it is going this side. Okay, then it goes like this, then it goes like this, and then it will tend to go back round and it will tend to circle. Now this is another kind of trap where it is caught and it keeps circling. It keeps moving in that circle, thinking that it has come out of the trap, but in actual fact it has not come out of the trap. Okay, because of the shape of the obstacle. So in this particular case, you should be able to check for circular motion, circular path. So path should not be repeated. So the way it is done here is path not repeated. So if it is repeating this path, if the robot finds it is repeating the path, it should not take that same path. It should change the path immediately. So for example, it should immediately change it to some other path and try this one now. Then probably it will come out from here. Okay. So new random start point, circular trap, then we have tangential force, random force. These are all combined together. Okay, depending on which one. Again, the question, which will work best? That's a difficult question. It is very much, path planning is completely geometry based. So depending on the kind of obstacle that is there, a particular method will work or won't work. Okay. Now, so far what we have been seeing, we talked about a robot that is essentially a point robot, but a real robot is not a point robot. So a real robot is not a point robot. Okay, that means it has some specific dimensions. So in that case, if I see a real robot like this, let's say this is my rectangular robot, real robot rectangular. Okay, so this is my x-axis, that's my y-axis. Now if I take this, then I have my center point xy, coordinates xy. Now suppose I say, as per potential field method, there is a force acting at that point, which is fx fy, and the coordinate of that point there is ax ay. Okay, then with reference to the base, to the global frame, okay, this is my global frame, what is the coordinate of the point? So phi is equal to, phi is given by, and the rotation of this robot is theta. The x-axis of the robot versus the global x is theta now. So the coordinate of that point is given by what? It is given by x plus ax cos theta minus ay sin theta. Okay, and y is equal to y ax sin theta plus ay cos theta. Okay, so we are seeing that the force which is acting at that point ax and ay, okay, can be converted to the global frame in terms of moment by using this Jacobian. Okay, we know that f tau is equal to, sorry, let me write, tau is equal to j transpose f. Okay, those of you who have not studied Introduction to Robotics, the statics part, please refer to the textbook regarding this relation, that the joint torque tau is equal to J transpose into F. Okay, and from here what we do is I take the derivative of phi and I get J, and if there are three variables x, y and theta, so first I take the derivative with respect to x, then with y, then with respect to theta. Okay, and what I get J is like this. Now I get this, my torque, which is equal to tau, is equal to J transpose into Fx, and the final relation we get is this. So this is the moment which is acting. So this is my moment which is acting at the origin of the global frame. Okay. Now by doing this, why do I need to do this? Because in the case of a real robot, you would understand that the forces would be acting at different points. So a real robot is not a point. So suppose I have a rectangular robot and there is an obstacle here. This fellow is pushing at this point. Okay, and there is another obstacle there which is pushing at that point now. Okay, so now you see that the robot is subjected to two forces at two different points, and the forces could be different. So we can convert it to a moment and then add them up and see what is the net resultant force which is acting on the robot. Okay, so this is the method used for converting the force acting at different points on a real robot, either it's a serial arm or on a mobile robot, to convert it so that we can convert to the moment acting at the origin of the global frame and then add the moments. Okay, so today we will stop here. What we discussed today is the potential field method, in which we talked about assigning potentials to, so we were assigning potentials to the object, the robot and the obstacle, and then the robot was subjected, at every point in the workspace the robot is subjected to a force in a particular direction, and then it effectively moves in that direction. And in this method there are constants, which is zeta and eta, okay, which we have to define manually, which will determine what is the force acting on the robot. Okay, so we'll stop here today and continue in the next class on potential field method.